Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. In the last lecture, we started off by discussing the quantum mechanical solution for one of the simplest systems, that is particle in a box. We formulated the Hamiltonian of it, and then we came up to the eigenfunctions and the eigenvalues of the problem. We would start from that part. Just to refresh your memory, we got energy E n as a function of n square h square 8 divided by 8 ml square. You remember L is the length of the box, m is the mass of the particle, h is Planck's constant, and n is an integer that goes from 1 to 3 onwards. N equals 0 is not allowed. So, the lowest value of n that is allowed is 1. Similarly, when you look at the wave function psi n, with this term 2 by L under the square root is the normalization constant, and then the wave function's functional form is essentially a sine function, which again has x is the dimension of the problem, L is the length of the box, pi is constant, and n is the integer that goes from 1 to 3 onwards. So, in today's lecture, we will actually have some more analysis or some more discussion on the solutions that we got from the last lecture. First comes the energy levels. E n equals n square h square divided by 8 ml square. So, here I have one y axis that would be for energy. If I put n equals 1, then I see E 1 will be h square by 8 ml square. To remain consistent with our previous notation, this should be capital L. E 1 is h square divided by 8 ml square, the mass of the particle, the length of the box. So, if you see for a given problem, when I know what is the mass of the particle and what is the dimension of the box, this entire quantity is a constant, and this value is called 0 point energy. So, this is the minimum energy that the system can have, the particle in a box can have. So, this energy is E 1, that is called 0 point energy, that is the lowest energy that is allowed to have. So, in this case I call this equals 1 at 1, this is my E 1. In the same way, if I look at E 2, what would I get? It has n square. So, 2 square is 4 h square divided by 8 ml square. So, I am simply writing it as 4 E 1. So, if the lowest eigenvalue is here, the next eigenvalue is somewhere here. This is n equals 2, this is n equals 1, and this next one will be E 3, which is, you can already see that n square is 3 square. So, 9 E 1, where n equals 3. One thing that you notice is that only allowed energy levels are E 1, 4 E 1, 9 E 1, where E 1 is a constant, that is the 0 point energy, and it is a constant for a given system, for a particle with given mass confined to a box of length L. All other values of energies are not allowed. This is what quantum mechanics gives us. If we had treated this same problem classically, all energies would have been allowed, because in classical mechanics the energy is a continuous quantity, but in quantum mechanics the energies are discrete, and in this case they have n square dependence. As you can see, I can go n equals 3, 4, 5, 6 and so on, and I would get the energy, the excited state energy of this system. The other thing that you notice here, the energy levels are actually not equally spaced. So, the energy difference between two consecutive energies, they keep increasing as we go n higher n. So, this is about the eigenvalues or the energy levels. Now, we will discuss about the wave functions. The wave functions general formula is given here. So, psi n equals 2 by L sin n pi x by L, where n goes from 1 to 3. We would first analyze the few low lying wave functions. For example, let us start with n equals 1, the lowest value. When n equals 1, psi 1 is 2 by L under square root sin pi x by L. So, this is my particle in a box, goes from 0 to L, this is my x axis. So, you can see when I have x equals 0, the wave function psi 1, x is 0. So, this is sin 0, the wave function is 0 over here. When x is L, this becomes sin pi, again 0. So, at two boundary regions, the wave function is 0. If you remember, this is coming because we made sure that the wave function is continuous all throughout the range of x from minus infinite to plus infinite, and you remember the wave function was 0 in the left hand side of the box as well as in the right hand side of the box. So, therefore, at the boundary of the box the wave function must be 0, and which is the case here. Now, at the middle of the box, so suppose x equals L by 2, when I put in this equation x equals L by 2, you would see that this is L by 2. So, L will cancel out, and then I will be left with sin pi by 2, and that is 1. So, therefore, when I multiply that with 2 by L, so I have that value over here. So, the wave function is 0 at the two x equals 0 and x equals L, and it has the finite value at x equals L by 2, and you see the sine function would have a dependence like this. So, this is the wave function for the lowest wave function when n equals 1. For n equals 2, the wave function is so again I have x going from 0 to L, but here the function over here is not pi x by L, rather it is 2 pi x by L. So, let us see when I put x equals 0, what do I get? When x equals 0, this becomes sin 0. So, the wave function is 0. When x equals L, this becomes sin 2 pi, that is also 0, and when x equals L by 2, so x equals L by 2, then this function becomes sin pi, that also is 0. So, at x equals L by 2, also the wave function is 0. Now, let us look at when x equals L by 4. When I look at x equals L by 4, I have the function sin pi by 2, and that is 1. And similarly, when x equals 3 L by 4, if I put it here, then it would become 3 pi by 2, that would be minus 1. And then when I plot this wave function, I will have something like this. So, what do I see? At x equals 0, the wave function is 0. At x equals L, the wave function is also 0. That I know because of the continuity, because I have imposed the continuity of the wave function. What I see additionally in this wave function, that even at x equals L by 2, that means at the middle of the box the wave function is 0, and this is called a node where the wave function becomes 0. Now, this is the wave function. Again, I would remind you, the wave function contains all the information about the system, but it does not have a physical meaning. What has a physical meaning is the probability density, which is given by the psi star psi, and this is what we are going to discuss next. So, here in the right hand side we would plot psi 1 star psi 1. So, in this case it would become 2 by L sin square pi x by L. We do not need to evaluate the sine function, we simply have to have the square of this quantity, this function that you see in the left hand side. So, this is my psi star psi, that means the probability density at different region of the box. X goes from 0 to L, and this is the middle of the box L by 2. I see that the probability density is the highest at the middle of the box, x equals L by 2, and the probability density decreases on either side. When I do the same for psi 2, I have psi 2 star psi 2 equals to 2 by L sin square 2 pi x by L, and when I take the square of this function, you would see. Okay, so this function did not look very symmetric. Let me try to adjust. All right. So, this is 0, this is L by 2, this is L. You can see both the negative part and the positive part, they become both positive because I am taking the square of the function. So, what do I see here? That I see that the probability density at the middle of the box is 0 when n is 2, but if you remember, the probability density at the middle of the box was the highest at when n equals 1. In case of n equals 2, the probability density is actually highest when x is L by 4 or x is 3 L by 4. So, this has a different probability density distribution for at n equals 2 compared to what we have for n equals 1. So, we would try to go further in our discussion, and in this picture what you see is that the wave function in the left hand side and the probability density, which is the absolute square of this wave function, in the right hand side. For n equals 1 and n equals 2, we saw in the previous slide, and we determined them explicitly, but now in this picture you can see also for n equals 3 and n equals 4. What do you notice here? That as I go higher in n, number of nodes that I am observing keeps increasing. For example, here this is one node point, here I have got two nodal points, n equals 4, I have got 3 nodal points. The nodal points are the points where the wave function vanishes, and therefore, the probability density at that point becomes 0. That means, you can never find a particle, you can never find your particle at that position. The other thing that you notice is that when you come to the probability density plot, you see that I have two regions where the probability density is high when n equals 2. In when n equals 3, I have 3 points where probability density is the highest, and as I go higher and higher, I see that more and more number of points I would see where the probability density is becoming very large. Remember, if I continue to plot this, continue to sketch this plot for a very large value of n. So, when n goes to infinite, you can already imagine that I will have the length of the box fixed, because for all the cases the length of the box is fixed, which is finite. This goes from 0 to L, but since n equals n is very large. So, I have many waves confined to the same region of space. So, therefore, I will have practically a situation where I would lose the so called discrete nature or the nodal structure over here, and then I will have probability density constant throughout the length of the box. So, this goes when n goes to infinite, the quantum mechanical particle starts behaving like a classical particle. There is no nodal structure here, everywhere the particle is allowed to be present. So, this goes by the name that Bohrs correspondence principle. This tells that for a quantum mechanical solution, when we go to large values of n, the quantum mechanical solution behaves more or less similar like the classical solution that we have, and in this case we saw this to be the case. All right, we will continue our discussion further. Other property that we already know, that the Hamiltonian that we solved is a Hermitian operator, and we also know that the Hermitian operator's eigenfunctions have to be orthonormal. So, we have already shown that the wave function that we had, the eigenfunction that we had was normalized. So, now the next task we have is that to show that the wave functions that we are getting are actually orthogonal. So, to do that we would take two different wave functions. So, how do I do that? I take psi n, which is 2 by L sin n pi x by L, and then another function psi m, which is and when I want to show that they are actually orthogonal, what do I mean by that? I say psi n star psi m dx going from minus infinity to plus infinity is 0. But I know that psi n and psi m are 0 between minus infinity to 0 and between L to infinite. So, therefore, this integration limit can be rewritten to 0 to L, because within this region only the wave function is non-zero, otherwise it is 0. So, then I have the term and I have to evaluate this integral. To do this, I would give you a general formula which is given here. If I have an integration bit of for sin a x multiplied by sin b x, the resultant solution is given here. So, I will use this formula to solve my problem. So, a plus b and this function has to be evaluated at the two limits goes from 0 to L. When you use x equals L, at x equals L, you would see that this function becomes sin m plus n by into pi, which is sin an integer, since m and n both are integers. So, m plus n is also an integer. So, therefore, this is sin n pi, which is 0, and m minus n is also an integer. So, therefore, this function also is 0 at x equals L. At x equals 0, does not matter what are the values of m and n are, since x is 0, this part becomes 0 and sin 0 is 0. So, therefore, at both the limits 0 as well as L, this function as well as this function they vanish. So, therefore, when I evaluate this, I would get 0. So, this explicitly shows that the wave functions that I determine for particularly in a box problem, the eigenfunctions that we have, they are actually orthogonal. So, we already have shown, so we showed that the wave functions are orthogonal, and we have already normalized the wave functions. So, together I have constituted the orthonormal set of eigenfunctions for the particle in a box problem. Okay. Now, we would evaluate some properties of this wave function. The first property that we would evaluate is that what is the expectation value of the position. So, if you remember the expectation values of any operator, so in this case it is position operator. So, we write the expectation value in this way. Expectation value of any operator is simply given as psi n star x psi n dx. So, this is the place of the operator x, the operator position operator is x, whose functional form is simple x. Now, I have to integrate it over all the range of space minus infinite to plus infinite, but I already know that from minus infinite to 0 and 0 L to plus infinite, the wave function becomes 0. So, therefore, I have only to worry about this range between 0 and L. So, when I use this form, so I have 2 by square root over 2 by L for each of the psi n and psi n star. So, when I multiply the 2, it becomes 2 by L. So, I am left with sine square n pi x by L. Okay. So, I have to evaluate this integral. What I would do is that I would of course, you can get this you can evaluate this integral in many other ways, but what I would take one particular approach where I define a variable u as n pi x by L such that du is your n pi L dx. When x goes from 0 to L, u would go from x is 0. So, u is 0, and when x is L, u will become n pi L by L. So, n pi. So, therefore, I can write this equation in terms of L as 0 to n pi. Sorry, I am writing this instead of dx, I will write it in terms of du. So, x will become L by n pi u, and the next quantity is sine square u, and dx will become L by n pi du. So, if I solve this, I have 2 by L by n pi square 0 to n pi u sine square u du. The reason why I brought my integral to this particular form will be apparent now. I am going to use this general formula for this integral when it is given as u sine square u du is shown here. So, I am going to continue my discussion in this region. 2 by L by n pi square, and I have u square by 4 minus u by 4 sine 2 u minus 1 by 8 cos 2 u, and this all three functions I have to evaluate at the two limits 0 and n pi. When you look at this function, so u goes from 0 to n pi. So, cosine function will go from cos 2 n pi to cos 0, both are 1. So, therefore, this term will become 0, cos 2 n pi minus cos 0 is 1. Similarly, sin 2 n pi minus sin 0 will again become 0. So, these two terms, second term and third term, will not contribute me to anything. So, I am left with only this the first term, and when u is n pi, I have u square as n square pi square, and when u is 0, then this term becomes 0. So, essentially the integral evaluation becomes much simpler. So, when I look at this n square pi square, they cancel out, L square, L would cancel out, and I will be left with L by 2. So, what this tells, that the expectation value of x is L by 2. Does it depend on the n? No, it is independent of n. Does not matter which eigenfunction I am, the average value of position operator, the expectation value of position operator for particle in a box problem is going to be L by 2. What does this mean? This means that the average position at which I am going to observe the particle is at the exactly at the middle of the box. There is a paradox here. If you remember your probability density plot for n equals 1, in that case you actually had n equals 2. So, this is psi 2 star psi 2, you had at L by 2, your probability density was 0. So, this is a paradox here, because what I am telling here that the average value of the position operator is going to be L by 2, whereas the probability density at the middle of the box was was 0. So, how do I resolve this issue? Please remember the difference between the expectation value and the probability density. The probability density at L by 2 is simply says that if I prepare the system in 10,000 different copies and make one measurement, I would never ever get to observe the particle at L by 2. But if I make an observation of all 10,000 systems and determine where I am observing the particle and then take their average position, I may end up getting average value as L by 2. To give you an example, in a class of 50 students, at the end of an examination, the 50 students get individual marks. Someone gets 30, someone gets 40, someone gets 50, someone gets 55. And if I take the average marks of the class, it may turn out that it is 60.35. The average value is 60.35. It does not necessarily mean that most number of people have 60.35. In fact, it may happen that nobody in the class has 60.35 marks, but the average value can be 60.35. So, this is what the difference is. When I say the probability density at a particular position, I mean that if I make many measurements, what will be the outcome of that measurement. When I say expectation value, I say that I do these 10,000 measurements, take the average value of it, what would be that average value. The expectation value is the average of many observations I made by preparing the system, preparing the identical systems in many copies and making many experiments on them. So, just to summarize what we did in today's lecture is that we started with the solutions that we obtained from our previous lecture, the wave functions and the eigenvalues and the eigenfunctions, and then we saw that the wave functions are in fact orthonormal, and then we evaluated an important property, that is the expectation value of position operator. The position operator expectation value turned out that the average position of the particle would be at the middle of the box, that is L by 2, but there exists an anomaly here that for some wave functions you would see that at x equals L by 2, the wave function vanishes because there is a node and the probability density is 0. So, I hope I made it clear what is the difference between probability density and how one correlates it with the expectation value. The remaining part of the discussion will continue in the next class. Thank you very much.